Hello again. This is Mark Summers from Summers Technical Services. We're going to continue with our series on doing shear and moment diagrams for beams using several different approaches and calculations. They're done traditionally, and we're going to do some computer simulations using Solidworks and some other tools. So this particular session is going to be using SolidWorks. Usually I use this as a three-dimensional FEA tool, but we're going to use it as a 2D tool to make the calculations much easier. We're going to be using a 3D model, but using the 2D analysis capabilities so we can extract reactions and shear and moment diagrams from our beam for use later for some calculations on deflections and shear stresses caused by the shear forces and normal stresses due to the bending moments. So let's get started. So here's our beam, and I've already created the CAD model, but it's pretty simple. I've just got a ASTM 836 material for my beam. And for beam moment diagrams and shear diagrams, the shape and material of the beam won't matter, since we're just calculating forces and moments due to the constraints on the beam. But I've got a model here of some kind of a shape, some kind of a W-shaped I-beam. This happens to be a metric I-beam. And these are in the Steel Construction Handbook. All the dimensions for these things are all listed in here, so we'll be learning more about that in class, about how to find those different shapes and the prevalent or the relevant dimensions. So what I've done is made a model here, and I've got three separate bodies here. And so normally when I do extrudes or any kind of feature, I check this box here. It says merge result. What that does is just make one big solid model on every feature you add. It just adds on to the original model. But here I turned off merge result so I can have separate solid bodies. So there's the first extrude, and if we pull over a little screenshot here of the beam loading, this is a 6 meter long beam. And so I've broken it up into a 3 meter long piece and then two 1.5 meter long pieces, so I can put the loads and the constraints on the beam. And so this is where those values come from. Drag that over here. So there's 3 meters and then two 1.5 meter beams. All right, so the first thing we'll do is, now that we've made our model, is to go to the simulation module. And once you do that, if that's not loaded, you just say Tools, Add-ins, and you can turn on your SolidWorks Simulation module, assuming you've got it installed on your SolidWorks installation. So I'm just going to click New Study, and I can give it a name here if I want. Maybe I'll call it Shear Moment 01. We've got lots of different options out here. We'll maybe make some videos in the future doing some of these other types of analysis, but this is just a static analysis on our beam. So we'll say OK. Now what we're going to do is we're going to go tell SolidWorks that we want to not simulate these beams as three-dimensional objects, but instead simulate them as real beams. And so I'll come over here somewhere and find these three different solid bodies. I'm going to select the first one and then control click the next two. Right click, and I want to say, where is it? Treat selected bodies as beams. So when I do that, it puts a node at the centroid and runs across and defines those nodes at the interfaces between these different pieces of beams. So that looks good. If I look at this joint group, right click, edit, I can see those four nodes it created. And there's some options in here, but I'll leave these as they are. And maybe I'll turn on display neutral axis. That seems like a good idea. So I can see a representation of the neutral axis where the stress due to normal stress due to bending moments is going to be 0, and where the shear stress due to shear forces is going to be a maximum. So it just shows the neutral axis in the display there. Alright, so now I've defined the nodes. Now I'm going to come over here to apply material. The model has already been assigned materials for these different pieces of the beam. So it's assuming, but I need to, I've assigned it in the model, in the manufacturing model over here on this tab. But for the analysis, I need to define it so it knows what material properties to use. So I want to find that A36 steel material, and it's got all the values here for elastic modulus, tensile strength, all their relevant properties. So I'll select the material, say apply, close. Okay, now what's the next step here? I need to apply a set of constraints on both ends. And so I want to say fixed geometry. And I'm going to go look at my PDF file we had a minute ago. Pull it up. Or my, where was it? Some kind of screenshot here. Here we go. So on this end, I've got a hinge joint right here. So this is going to be constrained in X and Y and Z from translation. But it's free to rotate about all three of those axes. And even though we're doing a 2D analysis, it'll ask us for all three directions. So I want to constrain it from translation in 3 directions and from rotation in all 3 directions. So I'm going to select this node here. Here's the joint, and I'm going to make it immovable because I want it to be able to rotate with just no translation. And so I'll say OK. And so I've got that constraint on this end. Now I'll do another one and go another fixed geometry, and I'll grab this node over here. Now this node over here is going to be a little bit different. I've got, if I can find my screenshot again, over here I've got a roller joint, and so it's not free to move up and down, but it is free to move left and right. So I need to tell it to constrain that differently. Oops, I don't want Google. So there's a joint. I want to make it movable. Well, actually I'm going to use reference geometry. What I want to do is I wanted to tell it I don't want no translation. I do want it to move in the X direction. And so what I'm going to do is define a direction with this box down here. This is going to define the direction. And I want it to be able to be movable in the X direction. And so I'm going to use this front plane to define the direction. Whoop, no, not the front plane, the right plane. So this direction, I want it to be able to move. And so perpendicular to that direction would be this button down here. So I'm not going to select that one. That one I want to be able to have it move on this end in the X direction. But the other two, I want it to be fixed. So I'll click these 2 buttons and tell it I want no motion in these 2 directions, but in the perpendicular direction, normal to the plane, I want it to be able to move. So I'm going to leave that one dimmed out. And these down here are also going to be dimmed out because I want it to be able to rotate about all 3 axes. So there's my constraints for this node over here, or this joint, it calls it, I guess. So I'll say OK. So I believe my constraints are set on both ends. Now it's time to add some loads. And so I want to say force. And again, I'm going to come look at my loading diagram here. I've got force 1 here that is, what is that? 10 kilonewtons. And that's on this end over here on the right. I'm going to drag this out of the way. And so on this node right here, I want 10 kilonewtons going down. So I want to choose a joint, and I want to select that joint right there. And it chose it there, it calls it joint 8. And I need to define a direction. And again, I want to use, this time maybe I'll use the top plane. I want to go perpendicular to the top plane. And so I'm going to choose a force normal to that plane. And that force is going to be 10 kilonewtons, so 10,000 newtons. And do I need to reverse the direction? I think so. The little symbol is so tiny there, I can't really see it, so maybe I'll come over here, make the symbol a little bit bigger. There, I can see it better. So now it's going down, I believe. So let's say OK. And let's look and see what it shows down here. There it is right there. It looks like it's going the correct direction. So there it is right there. Now what I need to do is define a linearly varying load on this left 3 meter piece. And this is a little tricky, so I'm going to figure it out. So on the left side here, the far left end, it starts off at W1, which is 6 kilonewtons per meter. And then it drops off to 0 at this 3 meter point. So I need to somehow define that linearly varying load. So let's see what happens here. So I'm going to go external load advisor. I want to say force, and I got to find the right option here. I don't want to apply it to a joint. I want to apply it to a beam. So I'm going to select this beam, and I want to define a direction again. So the direction I think is a good one is going to be this top plane again. And I want to do it per unit length because it's kilonewtons per meter. And I want to do a non-uniform distribution. So there's triangular, there's parabolic, there's something else, elliptical. I want triangular. And I want to define it to be perpendicular. I want forces, not moments, so I want to go perpendicular to the plane. And I want it to be negative 6,000 newtons per meter. It's minus 6. It's going down, so it's 6 kilonewtons per meter. I'm going to define it as minus 6,000. And somewhere I've got to be able to tell it not a total load, but I want it table driven because I want to have different values at different points. So I change that to table driven. And at 0, at this left end here, I want it to be minus 6,000 newtons per meter. And then over here on this second point, I want it to be 0. I want it to go from 6,000 to 0. And for some reason it doesn't like what I'm doing here. 0, and this should be 100. So did I get that right? There's the one I put in first. Here's this one for the beam. Edit definition. So what did it take there? Table driven, force. So at 0% is on the left here. It should be minus 6,000. What happened? This needs to be minus 6,000. The units are newtons. Well, I keep hitting enter and it keeps going away. Let's try this one more time. Table driven, per unit length, non-uniform, 0% should be minus 6,000. Guess I shouldn't be hitting enter maybe. There we go. Minus 6,000 at 0% on the left side here. and then it goes to 0 at the other end. It looks like it's backwards though. See how it's starting from 0 going this way? So let's flip the origin. There we go. So there I've got, looks like I've got 6,000 on this end, and it goes to 0 on the other end, which is what my little picture shows. Like this. So it starts off as 6,000, goes to 0. So I think maybe I got it right this time. I shouldn't have been hitting enter. I just need to click over on it. So, and I want to change this symbol thing so I can see it better. Maybe I'll change this to 400 so I can see it better. There we go. That looks pretty good. Starts off at 6,000 down newtons per meter, or 6 kilonewtons per meter. Goes to 0. Then it has that fixed load here. And here it's got the constraints on the end. So I think I've got it. So let's go over here to the mesh. We'll say create mesh. And boom, it's got a mesh. And again, it's not making a 3D mesh, it's a 2D mesh. And so that's the default size mesh. So if I wanted to tweak it, I could change some of the parameters and make it finer or more coarse, but we'll live with that. Now we'll say run this study. And it solves really, really fast because it's not doing any 3D mesh, it's just a 1D beam, and so it goes really fast. So here's some default results, and so I'm going to right click on results, and I'm going to ask for beam diagrams, and that'll pop up there eventually, I hope. And so I think I'll ask for shear force, and I never know which direction to ask for. So we'll just try direction 1 and see what happens. So it's asking for all the beams and say OK. So here is the, it doesn't look very exciting. Looks like very small numbers there, like 0. So it must be the other direction I want. So edit definition, and I'll change it to shear diagram for direction 2. And then see what this looks like. Oh, here we go. All right, so this looks good. It's got a shear value going down, and if we look at the hand calculations that I did in the previous video, we'll drag this over here, and we'll see how this compares to what Solidworks is telling us. Now, this is the hand calculations we did before. And there is the shear diagram, so maybe I'll do a screenshot of this so we can kind of compare the two. So we'll grab this goodie here and get this out of the way. And so the left reaction was what? 10 kilonewtons. And if we look at the shear diagram, sure enough, the dark blue here, this is minus 10 kilonewtons. And it goes down on this parabolic curve here. It's actually upside down from ours. In other words, the sign convention is just the opposite. Negative is positive and positive is negative, but that's just a sign convention thing. So it goes from 10 and it tapers off down to 1 there at 3 meters. And that's exactly what this thing does. It goes down here to the green right here. This is about 3, and then it goes down here, and, or excuse me, at the 3 meter mark, it goes down to 1 kilonewton, like it does over here on our hand calculations. And then at this abruptly, at this joint here, it goes from -1, in this case, to +9. There it is right there. And that's what happens right here. It changes, it transitions, it goes down because of that 10 kilonewton load. And then it stays constant at 9 kilonewtons. And then it drops back off to 0 here. So this reinforces our hand calculations we did earlier. So now let's ask for the bending moment diagram and see if we get a similar good correlation. So I'm going to right click and say define beam diagram. I want to ask for the bending moment diagram, And I'll use this and I'll guess which one. Maybe it's moment about, not sure how those directions are defined. Probably need to look into that, but I'll try one and see. And the other direction is going to be 0. So if I get a bunch of zeros, I know I'm got the wrong one chosen. All beams, Newton meters. I'll say OK. And again, this is one that's got all zeros, so I must have chosen the one the incorrect direction. So let's go right click here, edit definition, and change it from direction 2 to direction 1. And oh, here we go. Okay, this looks pretty good. So here we go. We start off at 0. It's got this curved shape here, and it goes all the way up to 13.5 kilonewton meters. And if we look at our hand calculations again, let me do a screenshot. If I can find it here. Let's do a screenshot of the bending moment diagram that we went through on the last video. Right here. And I will do another screenshot and capture this bad boy. And then dispatch this thing. And so, yeah, other than the sign convention, I think the sign conventions are flipped. It goes up, it starts at 0, it turns up to this, following this equation. When it gets to the concentrated load here, it's 13.5, which is exactly what the red maxes out here, and then it drops back down to 0. So that hand calculations are exactly like we get here. And we can ask for other items. We can list the beam forces and the resultant force, and we can verify that the reactions are as we would expect, which I got with the hand calculations. So the main takeaway are these shear and moment diagrams, and we can do it using the hand calculations we did earlier, or the using Solidworks to get the same results. And as the problems get more complicated, using something like Solidworks is a better solution rather than having to do a bunch of hand calculations. So anyway, now that we've gone through the Solidworks solution, we'll go try another couple of other software tools that we can use to get the same kind of information. So we can do this with Solidworks now, and we'll move on to other software tools in the next video. So until then, take care, and we'll see you in the next video.